Hi, I am Maram Khatib, a postdoc at the Robotics Lab of Sapienza University of Rome. It's my pleasure to introduce our work about the task priority matrix at the acceleration level, collision avoidance under relaxed constraints. This work is done with my colleagues Khaled Al-Khudair and Alessandro Di Luca. The robot capability of handling simultaneously multiple tasks while guaranteeing continuous avoidance of collision in a human shared workspace is an essential feature in service application of robotics, as well as one of the enabling technologies for collaboration in industry. In general, we would like to avoid any collision while preserving as much as possible the correct execution of the main desired task assigned to the robot. For a kinematically redundant robot, this can be done with the usual null space projection method, where the joint commands related to collision avoidance task are added and projected in the null space of the main task. This method is simple and ensures a strict priority. However, it requires recursion from highest to lowest priority tasks and possibly back. Also, it suffers from joint velocity discontinuity during any change in the task priority order. Also, joint constraint couldn't be respected explicitly. The discontinuity problem can be solved using a suitable scaling factor to switch between the tasks smoothly. Using the SNS method, hard inequality constraints in the joint space are satisfied. The task priority matrix method has been proposed by Fabrizio Flacco to separate redundancy resolution from task priority handling. In this case, any change in the task priority structure requires only to modify the TPM matrix F, which contains a compact but complete information on the different task dependencies. Note that the TPM method returns exactly the same solution obtained by the null space projection. Alternatively, collision avoidance can be integrated in a unified optimization problem as an inequality constraint defined in the joint or task space, and solved using the hierarchical complete orthogonal decomposition. In this work, we extended the task priority matrix solution in order to get several improvements. Consider a set of L desired Cartesian tasks to be achieved in a specific desired priority. Be defined at the acceleration level. By defining the control law at the acceleration level, we eliminate discontinuity in the joint's velocity. Also, in this way, we allow the consideration of robot dynamics or any other additional task at the joint level. For instance, joint velocity or momentum damping to be included as a null space terms. TPM is a square matrix to be computed in a specific way to impose the desired task priority. The key tool of TPM calculation is to use the Gauss-Jordan elimination method, considering the bipot matrix RII for each corresponding desired task. The QR decomposition of the transpose of the augmented task Jacobian is the first step to compute the F matrix. The operation for computing the TPM are applied in place. Therefore, we consider the temporary matrix par F initialized to R. For the first priority task, only one step is required, where the blue block of rows is multiplied by the pseudo-inversion of its pivot matrix. For the remaining tasks, two steps are required. First, multiply the blue blocks of rows by the pseudo-inversion of its pivot matrix. Then, multiply the red block by the modified blue one and subtract the result from the green block of rows. As another example for the last task L, first step is to multiply the blue block of rows by pseudo-inversion of its pivot matrix. Then multiply the red block by the modified blue one and subtract the result from the green block of rows. Finally, the desired TPM matrix F is the transpose of the modified matrix bar F. Usually the Cartesian task for the robot end effector typically includes following a desired time-varying reference for position and orientation. In this case, the robot needs at least 6 degrees of freedoms. The number of joints used to accomplish such a primary task reduces the capability of the robot to fulfill it while optimizing its motion with respect to other desirable criteria. For example, for avoiding robot body collision in the workspace. In this case, a possible degrees of actual dimension of the primary task is preferred. Instead of considering the classical and complete three-dimensional orientation task, using a pointing direction reduces the task dimension by 1, while using a relative angle to the pointing direction will reduce the dimension of the task by 2. That is, we are left with one-dimensional task only for the orientation. In our work, the pointing task is represented as a cone, with apex located at the desired Cartesian point, with an apex angle alpha d and a unit axis zd. The end effector ze axis should belong to the surface of the pointing cone, in the equality constraint case. While using an inequality constraint, more relaxation can be done by allowing the end effector to pointing on the surface but also inside the cone. The standard definition of a collision avoidance task is overdetermined and requires 3 degrees of freedoms to be handled. Instead, we used a relaxed version where the dimension of the task equal 1. This is done by projecting the repulsive vector in its corresponding unit direction. Avoidance task derives the control point toward any point of a plane orthogonal to its repulsive direction. In order to control the robot end effector to achieve prioritized desired Cartesian tasks, while avoiding any collision efficiently, we summarized our complete approach as follows. The end effector collision avoidance is computed using the conventional definition and accumulated to the positional task. 2 danger threshold distance defined on control points along the robot body. 1 control point taken into account using the relaxed definition. Proper task priority assignment using task priority matrix at the acceleration level have been used. In our algorithm, if the obstacle is located in the first, the closest surveillance area, the collision avoidance tasks will be treated as the first priority task. If the obstacle is located in the second, the further surveillance area, then the collision avoidance task will have the lowest priority. In this case, if there are enough degrees of freedoms, the control schemes will prevent the robot to approach the higher danger region. For the end effector, the positional task is always considered as the main task, if there are no obstacles in the first surveillance area. Finally, the relaxed pointing task is considered as the second priority task. It can be added or removed from the stack of tasks, depending on the value of the relaxed angle. In the following, we present different simulation scenarios and comparisons using the KUKA LWR robot with 7 degrees of freedom. The robot should make an ellipsoid path while pointing to a direction parallel to the word frame positive x-axis. There are 3 obstacles in the workspace. One of them is located directly on the desired end effector path. For collision avoidance, 9 control points along the robot body were considered. First, we compare the results when working with commands at the velocity or at the acceleration level. When working with velocity commands, discontinuity in the joint velocities occurs at any change in either the desired stack of tasks or in the dependency among the tasks. In contrast, when working at the acceleration level, the joint velocities are smooth, without large or sudden peaks. Then we compare the performance of the 3-dimensional and 1-dimensional avoidance task. Using the conventional 3-dimensional repulsive definition, the robot gets closer to the obstacles more frequent than with the relaxed definition. This happens because the 3-dimensional avoidance task pushes the robot to move farther away from the current closest obstacle. In this way, the robot comes closer to other obstacles, repeating a similar behavior. Moreover, in the conventional case, there are not enough degrees of freedom left for joint velocity damping, so an oscillatory behavior can be seen in the joint velocities. This vanishes with the relaxed definition. A last comparison is made between equality and inequality constraints. In the pointing task, the red traces indicates when the pointing task is active. When using the equality constraint, the pointing task is always included in the stack of tasks, and the error should converge to 0, if possible. Instead, when using the inequality constraint, the task is excluded from the stack of tasks whenever the pointing error is equal or less than 0, the blue traces, leaving more dexterity to the robot. Our proposed approach has been evaluated also experimentally using a KUKA LWR robot and a single Kinect camera. With our efficient robot obstacle distance evaluation performed directly in the sensor depth space. 9 control points along the robot body were considered for collision avoidance of both dynamic and static obstacles. The robot end effector should regulate to a fixed Cartesian point, while pointing to a specific direction with a relaxed angle alpha less than or equal to 5 degrees. During the experiment, the hand of the operator and an object are repeatedly moved closer to the robot. The proposed approach keeps the robot far enough from any obstacle while exploiting the available redundancy to minimize the error on the desired Cartesian tasks for the robot end effector. Since the pointing has the lowest Cartesian task priority, the related error becomes larger when collision avoidance is activated. In our work, we presented the extension of TBM method at the acceleration level, including the consideration of robot dynamics. Robot redundancy is efficiently exploited by designing low-dimensional task constraints. A simple algorithm was given for an efficient task priority management. The proposed approach is faster and simpler than other task priority approaches. However, joint inequality constraints have not been considered so far. For more details, please refer to our paper. And do not hesitate to contact us. Thank you and goodbye.